Thanks for coming back after a break. I'm the speaker is Michelle, she's for health. Chris wears many hats, too many hats. Chris is a foreign academic for Mila. He's a professor at Montréal. He's a Canada CFAR AI chair. He co-leads a working group on AI safety with me, Joshua, with IVADO. He's a distinguished scientist at ServiceNow.
Father of children.
Father of children. Chris also is a juggernaut when it comes to research. My association with Chris is if there's any topic you can think of, he probably has authored a paper on it. So we're fortunate to hear from him today on LLMs, facts, lies, and agents in the real world. So
Thanks a lot. That's
great preparation for what I think you're about to see. So I'm going to talk about facts, lies, and agents in the real world. And when I say in the real world, at the end, we really will get to the real world. You'll see what I mean soon. Because I work part-time at ServiceNow, and some of this work was in collaboration with them, I'm going to show you the safe harbor notice for forward-looking statements. I'm not going to look that forward into the future, so we don't have to worry too much. But I am going to show you a demo, but it's not going to be a product. Perhaps it might, but we don't know. All right, so you may remember before ChatGPT captured the entire world's imagination, essentially, there was another system that was revealed by Facebook a few weeks before that. How many people remember Galactica? I was paying a lot of attention to Galactica because it was an LLM specifically constructed for science. And we had been looking in science and the application of LLMs to science for a long time. And it generated a lot of negative attention. And in fact, the blowback was so large but they ended up taking it offline within a few days. Somebody was looking at it and they tried interacting with it, and they asked it about accurate estimation of body shape under clothing. And it provided them with a plausible title for a paper and a plausible author for that paper, but it was completely imaginary. Okay, and this was perceived as being something that could be potentially very problematic if it were to get into the broader use, filling the literature with all these hallucinated things that don't exist. We have been working on some very similar kinds of research. We had one of the first techniques that was able to write the abstract for a paper using the algorithm described in the paper at a level where it looked pretty good. But we were already starting to see, while it was super coherent, it tended to hallucinate things. Like many people say they got state-of-the-art results in their experiments, right? So we would throw that in too, right? But not everybody has state-of-the-art results in their experiments. So what we've done more recently is we've really focused on the problem of how do you write a high-quality literature review. And so we have two papers on this. The one here, Lit LLMs for literature review, are we there yet? Is just accepted into TMLR. And there's an older version of that, about a year or maybe even longer, about the toolkit that we use to do this. And so in order to fix that problem, we break up that idea of creating a literature review into two steps. Now, of course, today, we all know about deep research. Who's used deep research with a hand? Who's used Notebook LM? Okay, so everybody kind of knows this now, but this is like a 2-year-old project. But we came up with a couple ideas to really increase the quality of this kind of system. The first is we search for papers that actually exist. So we're going to use the trick that's widely used now, RAG. So we're going to find papers based on an abstract or a sketch of an idea that you provide. And that's going to generate keywords. So then an LLM is going to be used to generate keywords. We're also going to use embeddings. And then we're going to combine those using a form of debate-based re-ranking. And many of you here are familiar with that kind of idea. You'll get arguments for why you should include this paper on your literature review, arguments against why you should include this paper on your literature review. Many of you who've written papers know that sometimes this is the subject of your argument with reviewer two. Why didn't you include this paper on your paper, on this other paper? And maybe one of these was the reviewer's own paper, of course. Usually they're hidden inside of a list. But this allows us to have a more scientific way of determining what we should put on that list. So it's a form of debate-based re-ranking. And we're going to be combining results from Semantic Scholar, Google Search, and we also use other providers. And then we're also going to be comparing with another way of doing that kind of re-ranking based on asking a model to permute the results in one shot. So you can do it as a debate pairwise, or you can do it based on permutations. And then we also use an important form of evaluation in this work, where we take the most recent machine learning papers from the archive, and then that's typically about 3,000 plus papers, by the way, and we evaluate these methods on that. We try to recover for one of those papers that is recently posted the list of papers that were actually cited in that work. And by using the most recent archive cut, we can eliminate some of those effects, because we can look at what was a cutoff point for these large language models, make sure they weren't actually training on the test set, which is absolutely pervasive these days and really confuses results. And then we're going to be doing some, I'll show you some Rouge and BERT score and Llama types of evaluations. And I'll start off with some precision at K and normalized recall at K results. And so if we see here, we start with the basic semantic scholar keyword search generated by an LLM. We get that blue curve on the bottom. If we add in the permutation-based re-ranking, we get a slight boost. But if we use debate re-ranking, we get a much more significant boost. So we really see quite an increase in the quality of these results by using this debate approach. Now, if we use these embeddings, we beat all of that. And if we use embeddings and debate re-rank, we get even higher. And if we create an ensemble, so we've used this now as essentially as a way of re-ranking or as a way of ensembling, we kind of get the best result. And that continues when we also do precision at K, and a similar trend, increasing the quality. Now, another component here, which is kind of interesting, have you ever debated with somebody who makes stuff up? We in Canada sometimes have this problem. Have you ever debated with somebody who makes up references? Like it doesn't even exist at all. Like it's just an anagram of their own name. That happens too, right? We would like LLMs, when they're engaging in a debate for re-ranking, because they have a mutual goal. We would like to have the highest quality literature review list possible. One is negative, one is positive, but they're going to argue with facts. Okay, so they're going to have to cite passages of text that justify why they are saying what they're saying about the paper. So if the paper that you're proposing to include had state-of-the-art results, you have to quote in quotes using the LLM, eat it, quote in quotes, spit it back. I think you should include it because they said they got state-of-the-art results, and here's what they said in quotes. When you do that, you can also detect if the LLM is making stuff up, because you can just string match it. And if its string match doesn't match, you reprompt it and it tries again. Sorry, that argument is not good because it's not based on reality. Go again. And if you do that, you can see quantitative improvement in the quality of the re-ranked results. So it's a nice quantitative way to see the impact of telling the truth. Second step, once we have that list, we'd like to use that list as a form of RAG. We're not going to use that naively. We're going to generate a plan. So we're going to tell the model via prompting to organize things. In the most recent version, we do this at a high conceptual level. The experiments that I'm going to show, we did it at a micro level because context buffers weren't as big. Now we can pack in a heck of a lot of information into the context buffer. When we started this work, they were smaller. So we did it in smaller chunks. And then we tell it, say on which line you are going to cite things, or we say at the beginning in this part of the literature review on theme 1, cite A, B, C, D. In theme 2, cite E, F, G. Okay? And we see when you have a plan, you get a level of performance is reasonable. If you ask the model to generate its own plan, you get a better result. If you do teacher forcing at the plan level, where you get to see the ground truth and say, at least we know in the first paragraph they talked about this, we get an even higher level of performance, which is a simulation of an interactive scenario where a person intercedes, the plan is written, the person says, no, I really want to cite this and this on these levels. And then when we compute the Rouge scores, obviously we'll get a better result. And it's also another way to remind people that you don't necessarily want to always use this kind of model in a fully automated mode. Oftentimes, as a scientist, you want to have some control over this. This allows you to control it at the planning level, and you simultaneously have more control, and you have more accurate results because it's citing stuff that actually exists. Same thing happens with GPT model class. Of course, the performance is higher. These are on the multi-X science data set. This is a standard evaluation, but it suffers from that training testing issue with large language models. So we get a similar result when we use our rolling evaluation technique, where we only use the more recent stuff on the archive. Similar increase in performance across both things. The overall numbers are a bit lower, but the trend is the same. We can also look at these results in a pairwise manner using the model involving a plan or the model not using a plan. And then we can ask people who are graduate students in machine learning, who know about this subject matter if they can detect a hallucination. And we can see a dramatic reduction in hallucinations when you use the planning approach, and even more dramatic overall reduction in hallucinations, of course, when you use a frontier grade model, GPT-4, as opposed to Llama 70B. And we also have a preference for the plan-based technique in general. And this is also available as an interactive system. So if you scan that right now, you can try it right now. The person responsible for this, Gaurav, postdoc, is ready to fix any bugs. So feel free to try it. I think I saw a hand up. There was a question. We're good? Go ahead. Yeah.
Automated metrics like the Rouge and Burst score.
Yeah.
How much faith do you have that those are giving you?
That's why we actually, in the first round, you saw that we only had Rouge scores. In the second one, we had a BERT score and a Llama score. Those are typically considered a little bit better because they actually have semantics. They're not just counting words. So it can be semantically equivalent, but totally different words. And those results are pretty consistent with the Rouge numbers. So we feel pretty good about it. And we also have people that have evaluated it by hand. Another question? Here.
But do you think that such a thing is a good contribution to the community? Because many people are already writing their literature reviews,
Yeah.
By searching the internet without really understanding, and doing it from your own.
So do I think it's good for the community? I think it's fantastic for the community because humans are extremely biased. When you're looking for something that's important in your area, where do you go? You typically go to the most famous schools and the most famous people, and you look at what they're doing, and maybe you do some searching, maybe you get past the first level. But when you have a system like this helping you, I'm not saying it should replace you, it's helping you. It might help you surface that paper from somebody in Europe at a very good school. It's been around for 2,000 years or 1,000 years perhaps, and it's actually got really good stuff. So I see it as being a way to sort of empower the small guy in a way. Go ahead.
So what about, because the model is fact checking on text, but sometimes we know that some papers like the claims in the text doesn't really match the results.
Yeah.
So there could be a tendency to kind of overclaim in the text to kind of get higher ranking.
Yeah. Well, that's very interesting. I mean, with an LLM, you can actually start to do things like with the debate prompting, you can apply the debate prompting at that level and say, does this logically follow from what was stated in the text? So it's a super interesting thing. And I think there's still lots of potential to add another level of quality check. And we'll come back to that theme in a second. So I'm just going to show you what the interface looks like. You put in your abstract, so you'll see the same thing if you try it. It does a search process. It's a lot like ChatGPT's deep research facility, except it's focused exclusively on academic papers. You can put your own papers into the mix. You can check the ones that you'd like to include from a long list, about 40 results. Then you have the option to generate this high-level plan, control the sampling. And then here's an example of what a thematic plan looks like. So even from this, I found this paper, citation number 1, which cited the original version of our work. And this is what the high-level plan said. We should take result 1 and 3 and creates the high-level plan. This is what it looks like when it's rendered. I'm not going to linger on this, but you can take a look at it for yourself. Of course, Notebook LM is a little bit like this. It has this concept of citations to passages of text, which you can pop up and see and verify. This is a very important component. I use Notebook LM a lot as I was just trying to get an idea of what other people are doing in this space. It's very, very useful to have much more confidence in the hallucination rate of the model. You can also upload multiple documents and talk with them. Of course, that's like the most interactive version of kind of this idea. A less interactive version of this is, of course, OpenAI's deep research, where it asks you 3 questions at the beginning, then it goes off, and it also doesn't just search academic papers, it searches all over the internet. So just to recap, debate re-ranking with attribution to citations of strings that support your arguments was found to be quite effective. We've used RAG, essentially, to find papers that exist, and it's a common strategy to increase quality of LLM's output. And we've used plans, instructing the LLM to cite specific papers on specific lines. But what about the fact that LLMs still suffer from hallucinations when they're drawing from their parametric memories? I mean, it's much lower than it used to be, but it's still an issue. And this is particularly acute if you ask it to do a biography of you, unless you are Yoshua Bengio, in which case it has no trouble generating an accurate biography of someone who is extremely famous. But if you're not extremely famous, even if you're moderately famous, or if you're a new graduate student, it definitely does a terrible job of creating a biography of you. So in this line of work with Aristide, who is here in the audience, you can talk to him after, and Dima and Alex Pichet, a former student with me, we've looked at this idea of, can we teach an LLM to have self-restraint? If you don't know what you're talking about, just shut up, right? Wouldn't it be great if people could do this too, right? LLMs should be able to do this. If you're not confident about what you're talking about, we should teach them to reduce the number of things they say. So what we do is we get the model to generate multiple copies of the same biography, multiple runs. Then we extract the atomic facts, of course, using an LLM, it's not hard to do that. Then we tell the model to assess itself, its confidence in each of those facts. And we basically take the ones for which we have a particular threshold of confidence. Now, there's a little bit more detailed mathematical analysis in the paper, but that's basically the idea. And then we can establish a threshold. So in a safety critical application, you might say, I only want you to talk if you're like 80% accurate, sure, or 80% confident that what you're saying is true. And you can relax that. And by doing this, we can trace out a Pareto front of a model which says more things with a little bit of drop in accuracy, or it says fewer things, making sure that what it says, it's confident that it thinks it's got that right. And not only can we do this as an instance of test time inference, we can also amortize this. We can burn this back into the model and then try it on new biographies for which we haven't done this procedure, and that improves the performance of the model. Okay? So we can improve the quality of the internal memories of an LLM through this kind of procedure, basically burning a whole bunch of GPU time to do this. This is pretty expensive, but it can be amortized, and we can improve the quality of the base model. But even if you've got your facts straight, that doesn't necessarily mean you can infer correctly with those facts. And so there's a classic problem in old-fashioned AI, which spawned whole programming languages. Prolog was often completely associated with this kind of problem. I tell you the family relationships between different people. Martha's the sister of Mary, their father's Bob, etc. And then you ask, oh, well, how is Mary related to Jane? Okay? And then you execute in a forward chaining or a backward chaining fashion these different relationships, and you find out, oh, there's no family relationship between person A and person B. We can dump that kind of information as essentially like a Prolog program in a very simple data structure kind of format. And we can teach a model to execute that. We can also go to mechanical Turkers and ask them to add some distracting information, like this is how a scientist thinks of a literature, right? A story with things that are unrelated to the facts that we're going to draw inferences about. But of course, that's where the interesting part of a story is. But for our purposes, it's all a distraction because we really just want to look for where in the story did somebody say Betty likes picking berries with her son's daughter. Well, berries are relevant, but okay, her son's daughter, we've got some information there. So we can then examine how well a LLM is able to learn to perform these kinds of forward chaining or backward chaining proofs. And as is often the case, the most exciting result in here, I'm just going to show you one from this paper. This was from way back in 2022, was the one in the very end of the appendix, where we had at the time, GPT-2 had just come out, and I wanted to see if we would get a different kind of result if we had a pre-trained model that was fine-tuned to do this. And indeed, it was quite different than the rest of the results. But what we found was that short reverse proofs gave us the best strategy for deriving the truth from this inference procedure. No proof at all is also another option. That performed quite well. Short forward proofs suffered from this interesting effect where we only trained it to do proofs of length 2, 4, 6. And it degraded significantly for the proofs of lengths that it did not see. So that was another interesting result. And all of this was actually a predecessor to what has now become extremely widely used, this notion of chain of thought prompting. Of course. And of course, everybody remembers this perhaps when the stock market was crashing because the DeepSeek folks showed that by doing reinforcement learning combined with chain of thought ideas, you can learn using RL and a little bit of supervised fine-tuning how to do much better at complicated inference tasks like mathematics, such as this kind of question. And of course, we weren't resting on our laurels. We were already starting to think about another situation where you have a vision language model, where you get to see a question such as the one here that my daughter is actually actively doing for her homework in high school. You have a triangle, you need to compute the angle that's in this part of the triangle. So you have to look at it, and then you have to reason about it and give a result. Now, of course, we also know LLMs are extremely good at rendering code. So another way to increase the reliability of an LLM is to say, don't just try to figure out how to multiply or subtract inside of your parametric memory and usual neural computations. Use a tool. But not just that, don't just use a tool. We're going to tell you about the tools that we already know are reliable and robust, just like we do in software engineering. Don't rewrite the routine that computes this quantity when you know you already have something that can do it. So moving along those lines, we were able to show that you can construct these ground truth data sets using a larger model. You can verify that the result of using the larger model that has access to more information actually works, use that as training data, and distill it back into a smaller model. Very similar to the things that they were doing with distillation in the, that's become a very popular kind of approach. The DeepSeek is one example amongst many. But we can see with a 7 billion parameter model, our geocoder approach can be far more accurate than even the mighty GPT-4. So that's helping us deal with reasoning in a more reliable way because we're relying on traditional software and manipulating software components that are known to be good. But we can also improve factual memories, right? In the same way that in the prologue scenario, you have a bunch of facts, you need to execute rules. An LLM can do both of those things. We've just seen, well, we can execute rules, replace that with software and code. What about the facts? Well, we can also improve the facts because in many situations, if you want to know something very punctual, like what is the time zone of Salt Lake City, you could fetch that from an LLM, and it's good to verify that it does know that roughly. We could also just query some kind of knowledge structure, like a knowledge graph. So in this work here, we explore the idea of having LLMs just constantly communicating to a Sparkle query generator, and then replacing the normal thing that you would put in a Sparkle query, a URI, with just a text description of what that URI should be. And then use LLMs to replace that with retrieval techniques with the correct URI. And if we do that kind of thing, we can take all of these models from T5 to Llama to GPT-4 to a much higher level of accuracy when they're trying to get their facts straight, which is kind of a reasonable thing for LLM to do. Of course, you want them to have base competency for key facts that they should just know in their parametric memory. But of course, in the world where LLMs are constantly communicating with tools, why would they not ask knowledge structures for traditional kinds of information that we know knowledge structures work very well at storing and accessing and manipulating? Now, we've been talking about the transition from large language models as just a piece of software you run to a full-blown agent. Now, running experiments with that is actually a little bit tricky. But there's a really nice way that you can explore that if you imagine your LLM as an agent operating in a text world. How many of you have played a text game? When I was young, played a lot of these. Zork was the one that I played. Perhaps you played that as well. There's actually a whole suite of these kinds of text games. Of course, the other kinds of video games like Atari generate a lot more attention. But in the world of LLMs, these are kind of interesting. Mainly, they're interesting because you can replicate experiments very easily. Your turnaround time, if you're in an academic lab, is quite quick. So here, we examined learning agents. And here's the part that I've talked with Joshua, and he kind of likes this compared to online RL approaches. We proposed an alternative to a decision transformer. A decision transformer is kind of a well-known technology where we're going to predict actions based on observations and condition it on a return or a return to go. And when we want to make decisions, we just use that decision transformer. So there's many different variations of this. Some of these were proposed by Alex Pichet and myself, and Igor Mordach. In this particular one here, we have a world model, and we have a model of what kinds of returns are actually plausible under our big LLM's current model. So we're modeling what is the distribution over potential returns to go using a state-of-the-art large language model. So we're modeling a numerical value into the future, and then we can do a lot of interesting things. We can say, well, what would happen under the at least finitely probable worst case scenario predicted by the model itself. we can exponentially tilt to the negative direction. Or we can exponentially tilt to the positive direction. We can say, of all the things that we think could happen in the future in terms of returns, bad things, good things, let's get the most likely good thing. We can exponentially tilt in the positive direction. So then once we've selected that probable, but maybe unlikely, but very good outcome, we can condition on that and the observations to choose an action. Conditioned on the action, we also have a model of the future. So we can say to the model, if this were to happen, what is the likely future outcome? Essentially, it's a world model leveraging completely the technology of a large language model. Yeah, question.
The same language model that's inputs into the text environment that's somehow modeling these results.
That is right. The nice thing about a text environment, the distinction between the state, the action, the observation is clearer and also a little bit blurrier compared to what we're used to, right? In the original formulation of a DQN with Atari, there's a little bit of a conflation of like, what is the state? There's like X. I prefer to use the notation X for the observation, but that was sort of manipulated as state. And here we have just text. Text gets eaten. I read with the description of the environment, right? Then I can interact with the environment. Well, that's just text, right? Then the environment comes back to me and says, oh, something has changed. This is what it is. That's also text. But we can make those distinctions by just calling them A for action. Those are the words that I say. O are observations. That's what the environment says. And we also have a model of return. And so if we compare all the different reinforcement learning techniques that have been thrown at that problem, none of them actually do much better than straight up imitation learning. But now, what's a reasonable situation to do learning here? This is a situation where we get ground truth demonstrations, and then we teach the model how to interact in that world from a ground truth demonstration. Now it's brittle because there's randomness in these games. There's a random seed, it changes. The game changes in the way it behaves depending on the random seed that you provide. And so when you run it again, of course it doesn't generalize. And so what was very important in this case is to take a few random steps off of these golden paths to teach the model essentially how to get back onto a path that is a reasonable trajectory towards the goal. So with a very simple procedure of collecting some demonstrations and wandering off those demonstrations and using exponential tilt, and it was not super sensitive to the particular value of exponential tilt, we could do dramatically better across many, many games in that setup. Now we've been talking about multi-agents. This work takes these ideas of language models as agents to yet another level. This is led by Martin Weiss, who just defended his PhD about 1 week ago, also in collaboration with Joshua and Bernard Scholkoff. This is very creative work. Martin wanted to say, what if you had an LLM operating as an agent in a marketplace of information? As we know, you can buy research papers through providers, or oftentimes it's also available on the archive. In a other kind of information world, not the traditional academic information world, you may have many different suppliers of information, and there's a fundamental paradox typically. For you to assess the value of that information, you have to see it. Once you've seen that information, you don't need to buy it anymore, do you? Right? However, if you have an LLM, it can serve as an agent on your behalf. And if it's appropriately audited, it can assess the value of that information. It can negotiate on your behalf, and we can guarantee, if you're the market operating it, that it forgets the information afterwards. And so this work examines what happens if we construct a marketplace for information. We have buyer agents, we have seller agents. They enter into negotiations with one another. On behalf of you, you may not have more than one agent. In fact, you could have a buyer agent which has a debate. One person who is on your team is very frugal. They don't like to pay for information. The other person is very interested in quality, like, you know, husband, wife, met two people, different objectives. It turns out in this situation as well, you can get improved results by using this kind of debate. So here's in the situation in this experiment, we have two items that have the same price. And the optimal decision here is that you either buy one or neither, right? Because they're non-additive. It's the same information, same price. You should just buy one. You shouldn't buy both. Turns out if you don't do this kind of debate prompting, you often will end up doing stupid, irrational things like buying both pieces of information. In this other configuration, configuration B, we have a different price. One option is now priced higher, and we'd like to buy the one that is the lower cost information that's the same. Again, the use of this debate prompting, again, effective. Now, this is in an information world that's relatively limited. You have access to a search engine. You can get documents. Essentially, it's very easy to execute that kind of experiment because it's just document corpus of papers, easily aligns with all these other kinds of paper-oriented things I've talked about. Of course, the future is going in the direction where we have agents that interact with the web, arbitrary websites. Siva, I may have talked about this already, has an excellent data set called Web Links, examining how well agents can perform these kinds of tasks, clicking and interacting with user interfaces. And in some hot off the archive press work, in collaboration with Siva and his student, we have a new benchmark out to evaluate the ability of LLMs to act as a judge. If you've ever worked with this kind of model, what you typically see is that just like humans who get angry about not being able to log in, and sometimes they just keep pressing the enter button and maybe break their keyboard, LLMs kind of do the same thing. They often get stuck in these loops where they keep on clicking on the same thing and nothing happens. So if you look at the trajectories of a web agent interacting with a website, one of the most common failure modes is that it just keeps doing the same thing over and over again. Sometimes it's a cycle with many steps, but it's essentially the same thing that you do when you get frustrated and something's not working. You just keep on doing it and you don't, maybe it'll work, right? So we have ways of assessing how well human assessments of trajectories agree with LLM assessments of trajectories. So we can assess whether the agent actually succeeded in the trajectory, whether it caused unintended side effects. Maybe it accidentally cleared its memory of its previous purchases on the site that it was interacting with, or maybe it repeats unnecessary actions. So this is an interesting benchmark to look at. And this idea of LLMs that are able to evaluate other LLMs is, of course, really exploding in interest. And initially it may have seemed like that's not a viable strategy, but many different lines of inquiry have shown that that is actually a very effective technique. Now, remember I said agents in the real world, okay? Interacting with the web is kind of like the real world, right? It's not really the real world. Here in San Francisco, you already know about intelligent agents interacting with the real world because you can just hop in a Waymo, which has essentially replaced those red trolleys that used to be completely associated with San Francisco. And let's just say we have, Teslas in Canada, but most people don't realize that those things actually have a full self-driving mode, which you can enable as long as you're supposedly holding on to your steering wheel, right? But you don't have to hold on to your steering wheel that long. You can take your hands off that steering wheel for many seconds before it says, okay, put your hands back on the wheel. So whether people realize it or not, there already are the equivalent of Waymos operating all over the country, okay? And so this is the kind of sort of existential risk that I think about much more frequently than other kinds of existential risk because it literally impacts me the second we walk out this door. There could be somebody driving with a Tesla in full self-driving mode. And so way back in 2022, we proposed this way to model future trajectories. And you may have been asking yourself, like, well, this is an LLM workshop. Why are you talking about self-driving cars? Well, it turns out that if you think about these trajectories as sequences of sets, each one of these entities that we've detected, and typically there's a perceptual pipeline that consists of bounding boxes, putting them around all the pedestrians, which are these cylinders, all the different cars, which are represented by other boxes. You can think about modeling into the future how all of those different entities are going to move. And you can model that with what we proposed, a sequential set transformer. In fact, there was a sequential set transformer with a latent variable that allowed us to capture the multimodality in a single stochastic variable. And then when we generated samples, we had clearly identifiable modes in that latent variable. Turns out we're very lucky that we were moving quickly on this. Waymo had a paper several months after, very similar idea. Tesla also revealed they were doing something very similar with transformers. But of course, everybody was doing stuff with transformers around that time because they were the cool kid on the block. But we can go further than that. If you recall this notion of return condition supervised learning with model-based return condition policies, we can now have a multi-agent environment where we're not just doing imitation learning by learning a sequence, we now have the ability to specify rewards. I would like the trajectory in which I kill no one. But we can also say the opposite. I would like the trajectory where the other people have gone off their rockers and they are behaving extremely dangerously. They're driving too fast, they're not stopping at the light. That's all completely possible by just exponentially tilting in the other direction. So by using this offline reinforcement learning formulation, we can construct worlds where we have a lot of crazy stuff going on, and we can train agents in those worlds, which would be very hard to train in if it were the real world, because you don't typically get much data in that kind of situation, real world data. Now, these models are much more sophisticated. I'm in an engineering school, and we like to do the problems somewhat for real. So we take in maps, we take in potentially other types of information as well, and then we roll out those trajectories as I've described. Of course, we had nice results, did much better than other things. But what was more interesting about this is our ability to generate these dangerous scenarios. With negative tilting, we can make somebody do a lane change where they didn't quite judge it right, and they're going to cut you off. And then we can learn agents that know how to slow down appropriately. Now, everybody was kind of excited about the ability to generate really cool images, like the Pope in a puffy jacket from a text prompt. But there's another kind of image format that's equally used and actually preferable in many contexts. That's vector graphics. So in some of our more recent work, we've been generating vector graphics from text or converting images into vector graphics. This is star vector, which was one of our more recent versions of this. The reason I'm showing you this is that vector graphics can also be used for the problem that I was just talking about. In this line of work, we use a diffusion model to diffuse in the latent space of an autoencoder model and generate new map configurations for which we've never seen before. So now we have the ability to generate synthetically arbitrary complexity street scenes as a vector map. And we have the ability to put agents in those street scenes, some of them acting a little off the rocker, and train agents to be robust into those kinds of situations. Looks like this: autoencoder, latent space, diffusion in latent space, vector graphics out. That's some of our most recent work to be presented at CVPR 2025, and we can generate arbitrarily complex stuff like that. Now, in some cases, almost done. Started at the top of the hour, right? In some cases, pixel level perfection is desired. I was just in Italy walking on roads which had no sidewalks, and I had to go from my hotel to another hotel. Let me just say, pixel perfect predictions seem like a pretty good idea when these cars are zipping by you and you have no sidewalk. In this example here, we have I love this example because it's a Mercedes-Benz. It looks like a crosshair. So we can see, as time goes on, exactly where that arrow on the road is relative to our car. This example here was generated by one of our models from this work, masked conditional video diffusion. And we can see very clearly how good the model is relative to the ground truth when we project many frames into the future. And so this work was at the beginning of a huge wave of interest on diffusion models for video. And I'm not just showing this because it's kind of a cool picture, showing you this because it's directly related to the AI safety thing I was just talking about. In our most recent work, we've combined those two ideas. If you have a high quality motion prediction system, you can project the bounding boxes of your prediction into the future into the ego agent's frame of reference. And then you can use that as a signal to control the generation of the imagery. And so I don't know if you can tell the difference. One of these is a synthetic image generated from these bounding box progressions. The other one is the ground truth. Can you tell which one it is? Top or the bottom? Pretty hard. Key is, if you have a high quality transformer-based predictor model, you can now render that down into a reasonable, plausible, high quality geometric scene at a level of complexity much higher than you would get from simple bounding boxes. You can do it from synthetic data. You can do it from synthetic data or real data. Here's another example. Can you tell which one is generated? Not easy. Here's another one. This is Control V. This is also another line of work which was just accepted like 3 days ago. It seems like I have like 5 different pieces of work here which were accepted 3 days ago, but I wanted to feature all of them because I need to thank my students who are the real rock stars making all this possible. But I also will just summarize some of the points here. So we've made a lot of progress dealing with hallucinations. You've probably seen it interacting with systems like ChatGPT. We're at a much higher level of quality for hallucinations than we used to be. The merger of traditional softwares and LLMs allow us to have reasoning operations offloaded to classical, symbolic, normal software, and we should use that. Similarly, we should also consider using long-term memory encoded in traditional knowledge structures. There's some people who kind of conjecture that LLMs couldn't reason. Well, writing complicated software is, I would argue, pretty good demonstration of reasoning. This is getting very real. When software is interacting with an autonomous vehicle or with websites, we're interacting with the real world. And in this talk, I focused a lot on really engineering and science solutions to make these systems more reliable and safer. There's a lot of crazy stuff that could happen in the future. I'm in an engineering department. Like it or not, I got to focus on those things. Responsibility is to protect the public about things that are about to happen or already happening, and I'll take that seriously. So in all cases, we need to be very conscious of the effect of out of distribution situations. And we've seen that, these simulations of cars in situations that are very hard to collect because most autonomous car companies don't release their accidents. That's an important thing to consider. And lastly, unexpected behaviors arising from agent dynamics is really at the horizon. We saw some other talks on that, and it's really something we need to be thinking about a lot, and many of you are, and I'm happy for it. That's it. Thank you. Yes.
We started at 10:15, so you do have 15
Oh my God.
minutes.
Well, I got 15 minutes for questions.
That's right. Ah, 15 minutes for everybody else.
Yeah. Oh, in that case, I'll say, go here. Yeah.
So I've actually asked you this before, but when it comes to the information market,
Yes.
information is a little bit unique, right, compared to other markets where you're buying goods, because you can actually get one bit of information from the exchange, right?
Yes.
You can ask a very precise question,
Yeah.
which is like, is the stock price of this thing X? And if it says, and you will buy it under those conditions, if it comes back.
Yeah.
Yes.
Just like if you were trying to communicate with your secret friend, you could do bank transactions for 2 cents, 1 cent, and somehow use RSA to communicate stuff. Sure, yeah.
Thought about like the implications since the last
Yeah.
time. Wondering if you thought of the implications of that.
Yeah, I think one thing you could do is you could enumerate all the different ways in which you could essentially sneak information into the system, and you add restrictions based on the market itself, stopping you from performing that kind of transaction. Like, request something and withdraw is one way you could implement that. There's other ways in which you could leak information with more sophisticated schemes. Yeah.
I was going to, the first part of your talk was more about curation through debate. Right?
Yes.
And my view is that curation is much broader than, say, just, doing things around papers and citations.
Mm-hmm.
Right? Because it is a kind of ordinal ranking. You can think of it as search as being a form of curation, for example.
Yeah. Yeah.
Very broad applicability.
Yeah.
And I was just wondering what your thoughts are around that. And then the second question is these probabilistic models.
Yeah.
Like, what is really out of distribution? Because everything seems in distribution for them.
Yeah, okay, so that's great. 2 great questions. So for the first one, there's a lot of nuance into how you construct a prompt for engaging in a debate. So the debate, that prompt can get very rich and sophisticated. So you can do things like say, I know everybody cites, the attention is all you need paper, but you're one of the person who's the champion for that could say, your paper is so, close to the fundamentals of an attention mechanism, you should still cite it. Even though everybody cites it, you should cite it because it's relevant to you. And so the arguments that one uses to determine what should or should not be included can be very nuanced. And it can also be in terms of like, Well, because if you give it sufficient context, at the time we didn't have it, you can also give it what is your current list. And so if you already have a paper that's covering a particular subject, the detractor might say, well, we already have a paper that's covering this subject, so we shouldn't include it on here. And so it's much more nuanced than you would ever get from typical kind of more simple heuristics for re-ranking things. And I mean, maybe they could get it, but they certainly wouldn't have this audit trail where you literally see the transcript of why something was or wasn't included. And you could imagine like your agent on your behalf re-articulates that to reviewer two, when reviewer two says, well, why aren't you citing my paper? You can say, well, we've already got this other one, and it was, my large language model agrees with me. So the other one is about out of distributionness, whether it exists or whether it's always there or not. And in that, the advantage of thinking about it in the way that we've been doing here is like you really can see it. So in the case of the generation of those videos, I'm not going to talk too much detail this, but we've done some experiments. And for example, if you have a car to the left, a car to the right, and you say, let's create an atom smasher or a car smasher, and we're going to give a trajectory that we've never seen, two cars smashing into one another. Okay, I don't know if I have it here, but that's never been seen in any of this data, right? Because all of the data doesn't have that. What happens is they disappear. So the way in which these models behave in these out of distribution settings is very important. Sometimes they merge and two cars become one car. Okay, well, that's a nice, fun, visually interesting way to think about it. But if your self-driving car didn't have enough of those kinds of examples of edge cases, I don't know if you want to be in the car when it merges with another car or they disappear, right? It might be you that's disappearing. So I think the notion of out of distributionness is actually very useful still. I think these models do have pretty well-defined notions of things that are out of distribution. And I think by using this exponential tilt trick in a multi-agent configuration, we can push in simulation those synthetic agents to explore regions of the out of distribution in training, but still plausible physical scenarios in a kind of systematic way, right? But you have to have a lot of pieces in place to do that. We actually have, I didn't talk about it because I was going quickly, we implemented a physics model in this situation. So the agents that we're working with, they aren't just magically teleporting from one place to the next. We did the very painful thing of there's a gas pedal, your agent has an action, it presses on the gas pedal. If the road is slippery, it doesn't go right away. If the road has other properties, it behaves differently, so it's been decoupled. So all of that can be captured and you can get these things. But even with that, you can have very crazy situations. Do I have the video? Let's see. Oh, I had a cool video, but somehow it's missing. Like, for example, another example is environments, like cold weather environments. In Montreal, we get snow that's up to here. So there's a notion of out of distributionness that you would just never, ever see in California. And it's kind of crazy to think that you would have a car that doesn't have extreme exposure to Montreal's snowbanks. I mean, it's as if you have like a sandbank at the side of the road that's obscuring half of the road, and it's dynamically there the next day because the snow plows have piled up so much snow. So this notion of out of distributionness is like definitely a real thing. And it's something that we can explore to some extent in simulation by going the full 9 yards to have a multi-agent simulation. Yeah, Tanya? Okay. Yeah.
So I just tried your tool.
Okay.
It's great, so it's I put an abstract for AI paper.
Yeah.
And it's not published, and it gave me more than half of its results, surveys and reviews.
Yeah.
So my question is, do you have any kind of plans to have a filter for the quality of?
Yeah. That's what's, of course, amazing about opening up this so that it's not sort of like, a closed version. Having prompts which say, I don't want literature reviews, super easy to add, right? You can just basically make one of those agents in the debate, be conscious of that, just changing the notion of the prompt, and that'll re-rank it. We're giving about 40 papers now, but it's being reduced from about 200, I think, in the background. And we could add that in as an option, or also just user-defined prompts. But as we all know, can't always let users do any prompt because they might do adversarial things. But if you send an email to Gaurav with that feature request, he is so good, it will be implemented probably before you come back from lunch.
But my question was more on figuring out the quality of information.
The quality of the information itself. Well, again, it's another thing you can totally do with an LLM-based prompt, right? You can assess the information density of a review. You can also say, I only want original research. And if it is, it's like a crazy world we live in. The amazing thing is you could say, if it is a literature review, open up the paper that's being cited and cite the original paper, not the literature review. That's all totally possible. It's just a question of implementation. Yeah, so it's, yeah, great idea, great points.
Yeah, this little LLM idea, right now, is it only fetching papers all at once? Or it realizes, okay, I read this new paper, now I have to go and fetch something else. This is what we do when we're writing literature review, right? Yeah. We know of one paper, but then when you go and read that paper, I miss citations.
Follow its citations. Yeah, exactly. For the experiments, we didn't do that, but for the operational system, that's totally something we can do. And that is definitely the kind of things that people do. I mean, a lot of times, many people's citations come from, there's a key paper, it has all the key stuff. It's essentially versions of a subset of the papers from one of those key papers that's relevant to your work. And that's the kind of thing that we see with deep research. It has, if you look at the audit trail of where it's going, it does appear to be following those links. And so it's something that just gives it a much more interesting kind of search behavior. So it's certainly something we're interested in.
So deep research in your observation was more adaptive, like it sees something and then again?
It seems like it's able to, but they only give you sort of a cryptic log of what's going on. So you have to sort of like infer what it might be doing.
Right.
It doesn't seem to be like explicitly saying that, but my inference is that it looks like it is based on the sequences. Like oftentimes it'll do things like it'll try to go to a site and it says, okay, I'm blocked from downloading this, so I'm going to try an alternative option. And then oftentimes there's a sequence of queries which appear to be linked. It's, yeah, definitely something we're interested in. One here, then do you want to go? I'll let you go.
So this is a bit more high level, but my experience with these summarization things, like
Yep.
there's something, I can't put it in precise words other than to say that there's something unsatisfactory about the experience where the summarization is not technically wrong, but it's also surface level.
Yeah.
That feels like regurgitation and not the way that humans give analogies and mental pictures to help.
Yeah. Well, so
I mean, I'm not even sure we should be improving these tools to the point where they can use analogies, but that's a different point. But I guess
sure.
my question to you is, have you thought about the sort of uncanny valley that they see?
Oh yes. So I don't want to go into too much detail on how to fix that problem. But yeah, it's definitely something we're aware of. But there's a very easy explanation for why it's doing that. And I'll just say it has to do with the fact that if you just naively eat the internet with an LLM, there's a lot of nuance into how you structure that data. Right? And if it's just paper after paper after paper, you learn about another paper indirectly, right? So if it's a famous paper like the GAN paper, you know what's in that paper from having read it. But you also know what's in that paper from all these people talking about it, right? And the way in which a lot of people talk about other papers is often at a surface level. So-and-so also did generative models, cite GANs, right? Few of them get into the meat and they say, well, it was a minimax game, et cetera. But drawing those connections together is, there's still research. It's to be done, thankfully. It's not just a question of eating a bunch of sequences and predicting them. There's a lot more you can do. I'll just leave it at that. Another question here.
Yeah, I just wanted to hear more about your physics-driven simulation engine.
Yes.
I actually friends who are on the second line. So, like, who's modeling hitting the deer?
Yeah.
And like the physics.
Yes. Yeah. So NVIDIA has a new video model, Cosmo, in which they trained it on a lot of that kind of stuff. Okay, but it's still not perfect, right? It's still got a lot of issues. But to some extent, the question is like a question of resource allocation. And if it is going to be the case that we will have a large number of autonomous vehicles deployed, not just here in San Francisco, but like globally, then the reasons behind why you might model physics of that particular situation at a much better level start to go up, right? And so I suspect the market will work in our favor in this situation where doing that becomes worth it. We already know for traditional automotive manufacturers, they run very sophisticated numerical simulations of metal squishing, right? That's like at a different level of granularity in terms of what we're looking for. What we're looking for is like, if there is a collision, like even with our models, it's a bicycle physics model. So when they hit, they go, okay? That's not what happens, right? So again, I don't want to talk too much about what we're doing actively right now, but like you've hit the nail on the head. Yeah, it's a real problem. And if you want a superhuman car driver that is like in some Hollywood movie, getting up on two wheels, like in a James Bond film or something, and getting around the problem at the intersection, wouldn't that be cool, right? Wouldn't you prefer that to the alternative, which is everybody in your car is dead, right? So as those end games start to become a real thing, maybe we'll get there. And it could be pretty cool, like seeing an autonomous vehicle save the entire family with some crazy maneuver. And that's only going to happen with this weird kind of simulation, because you're not collecting that data at scale, right? But it is possible. You could learn that by understanding the physics of the real world in the real world in situ situation. And we're actively looking at that. I'll say it, I'll leave it at that. There was another question here, maybe? Yes.
Especially for a lot of engineering heavy work that's focused on like current well-established reliability issues like hallucinations. My impression is that there's a lot of economic pressure on industry actors to make improvements there.
Yeah.
So I'm wondering about a question I have for a lot of talks, which is like how do you think about the problem of choosing directions that in academia that aren't going to be independently replicated by industry actors who are working on the same problem?
I'm a very competitive person, and I don't have a problem competing with full-on industry. So if it's doable and I see a path to get something out before industry, and I think my students are up for it, we'll go after it and we'll do it. And we've beaten the industry on multiple occasions. So I don't worry about that. I often talk about this situation, the dawn of quantum mechanics. Like one position you could take is like, I'm not going to do something other people are going to come up with, right? Because they're going to do it anyway. But like, it's not like Schrodinger said, oh, Heisenberg's got matrix mechanics for quantum mechanics. Why would I use continuous wave mechanics? Because he's done it. Or conversely, Heisenberg didn't stop, right? So I think you can actually, as an academic lab, compete on some of these things. Now, there's also things which are, by your constraints, necessity is the mother of invention. We saw with DeepSeek, because there was export restrictions on their compute, they had to do old-fashioned research instead of just scaling, right? We had to do the same thing. In that video diffusion paper that I described, we were able to get that out because of the trick that we came up with. The masked conditional video diffusion. Turns out, if you train a model as a pseudo ensemble by conditioning on the past and the future stochastically, the model converges way faster because it gets to see the easy problem, which is, here's the first frame, here's the last frame, what should you do in the middle? And the answer is, most of the time, copy it over and tweak it a little bit, right? But if you're only given nothing, and you say, do an unconditional diffusion model of video, it's going to spend a lot of time not knowing what the heck it should be doing because you've given it a much harder problem. So the fact that we were resource constrained meant that we had to think about ideas that would actually be more efficient, in this case, in terms of training dynamics, and that allowed us to get a model trained on academic grade infrastructure. And so I think the necessity is a mother invention is really true. Like you can still go after something that many people concede that's going to be possible in the next X months. Can we do it? Well, in an academic lab, if we are to do it, we're going to have to approach it in a strategically intelligent way. And that may actually lead to an innovation that's even better than had you just brute forced it. So I think that's my answer for that. None maybe? Yeah. Yeah, but thanks for the questions.
Yeah.